Chapter 4 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 4, The Forth Bridge. A glance at the map of Scotland serves to show that that country is nearly cut in half, towards its southern end by the firths of Clyde and Forth running inland from the west and east respectively. They find their counterparts in the Severn and Thames estuaries, which, in a similar fashion, interrupt direct natural communication between the southern and midland portions of England. The interruption is, however, more serious in the Forth than in the Thames, inasmuch as the intervening water space is broader, and because South Fife and the Lothians are proportionately more important than Kent and Essex. In the case of the Thames, too, the estuary has narrowed into a river long before large towns are reached, and the crossing, even in its tidal parts, is a matter of small danger or difficulty. Until recent years, a traveller in the east of Scotland, when desiring to pass from Edinburgh to the counties of Fife and Perth, had to choose between an inconvenient and sometimes stormy passage of the Forth in a steamer at Queensferry, and making a long detour by rail round by Stirling. The loss of time entailed, in either case, was a serious handicap to traffic between the counties north and south of the Forth. And at length it became so intolerable that schemes were propounded for connecting the banks of the Forth by a permanent means of intercommunication. As long ago as 1805, a proposal was brought forward to construct a double tunnel under the bed of the Forth, but matters got no further than the issue of a prospectus and pamphlet setting out the advantages of such a tunnel. 13 years later, one James Anderson, an engineer whose ideas and theories were on too large a scale for the engineering science of the time, suggested the erection of a bridge at Queensferry. The bridge to contain main spans of 1,500 to 2,000 feet, be 33 feet wide, and to cost the very modest sum of £205,000. The extant designs of the bridge make it clear that it was as well for any would-be shareholder that the scheme never passed beyond the paper stage. When, however, in 1860, the greatest originator of vast engineering undertakings, the railway, moved in the matter, things began to wear a more feasible aspect. The North British Railway planned a bridge about 6 miles northwest of South Queensferry on 500-foot spans. But the project was dropped, to be revived in 1873, when the Forth Bridge Company was formed to carry out the designs of Sir Thomas Booch for a suspension bridge with 2 large spans of over 1,600 feet each. The capital was actually subscribed, and an act authorizing the construction passed through Parliament. A commencement had been made on the island of Inchgarvie in the foundation of one of the great main piers, 550 feet high, when the work was suddenly stopped by the terrible disaster of the Tay Bridge in December 1879. Sir Thomas Booch, as the engineer of that ill-fated structure, lost the confidence of the company and the public. His designs were, therefore, laid aside, and investigations made into alternative methods of crossing the Forth. The committee of experts appointed to draw up a report abandoned, after due consideration, all ideas of driving a tunnel under the estuary, since the excavation necessary for the approaches on both sides would involve a very great outlay, and decided in favor of a bridge. In 1881, Messrs. Fowler and Baker, since honored with a baronetcy and knighthood respectively, submitted plans for a cantilever bridge of an altogether unprecedented size, to be constructed between North and South Queensferry. Before going further into an account of this mammoth structure, it will be well to explain the principle of the cantilever. An engineer, let us suppose, is called upon to bridge a gap of several hundred feet. How he will proceed to accomplish his task depends chiefly on the natural conditions of the locality where the bridge has to be made. If, for instance, there is dry land or shallow water on a hard bed below the gap, and the perpendicular height is not excessive, he may elect to build steel or brick piers a moderate distance apart and to lift onto the top of these girders of the truss type, each completed before being moved, and when placed in position independent of its neighbors, its weight being borne at either end by a pier. But when conditions decree that the points of supports must be few and far apart, the difficulties of our engineer are much increased. In the case of the Britannia Bridge, Stephenson built huge tubular girders of 460 feet length and hoisted them into position by means of hydraulic presses. But the difficulties to be overcome were enormous, and such a proceeding would be practically impossible with spans of 500 to 1,000 feet. When such are required, the engineer resorts either to the suspension type of bridge, to be seen at Clifton, Hammersmith, Niagara, Brooklyn, or builds out from his supports on both sides simultaneously in such a manner that the structure as it proceeds is in a state of balance. The balanced arms may be rigidly joined to neighboring arms in the middle of the span, and the connections over the piers severed so as to resolve the structure into a series of independent girders of the type first mentioned. Or a gap may be left, and this be bridged over by an intermediate girder resting at each end on the arms. In this case, the piers, or points of contact, are the centers of pairs of cantilevers, as the balanced arms are named. To make this quite plain, let us suppose two chairs to represent bases of two piers of a cantilever bridge. Men seated on the chairs are the towers. They raise their arms simultaneously, maintaining their vertical balance. A very small pressure would depress their hands, so they are provided with sticks, which they grasp firmly at the upper end and rest against the seat of the chairs. A weight now hung from their hands is borne by the power of the sticks to resist compression and the strength of the arms to resist extension. Our men are two pairs of cantilevers. Between them is, let us say, an interval of 2 feet. This is bridged by a board of proper length resting on the upper extremities of the two inner sticks. If a third man sits on this suspended girder, his weight causes his companions to lose their balance and fall inwards. So a couple of heavy weights are placed on the floor, immediately under the outer hands, and straps are passed from the anchorages over the hands. The cantilevers can now withstand the weight on the central girder without losing their equilibrium. This explanation made, we will return to the plans for the fourth bridge. Footnote: adapted from an illustration given by Sir B. Baker in a lecture at the Royal Institution. End footnote. On the north shore of the Forth, at North Queensferry, a somewhat triangular-shaped promontory projects southwards for 1.25 miles into the water. At a distance of almost exactly 1/3 mile south of the outermost point lies the small island of Inchgarvie, crowned by an ancient castle. Between Fife and Inchgarvie runs the main or north channel of the Forth, over 200 feet deep and more generally used by shipping than the south channel, equally deep and wide between Inchgarvie and the southern shore. There is on the south side of the south channel an expanse of shallow water 2,000 feet wide. The engineers erected 3 huge steel towers, each resting on 4 massive piers, on the extremity of the North Queensferry Promontory, the western end of Inchgarvie, and in the shallow water at the south edge of the South Channel. Each tower is 343 feet high from the piers to the summit of the steelwork, and a man standing on the ladder would be 361 feet above the high water level. From these huge supports, 6 cantilevers are built out, each 680 feet long. Those at the north and south ends rest on viaducts leading from the higher ground at a level of 157 feet above high water, the level of the permanent way. The other 2 pairs terminate while yet 350 feet apart, and these intervals are bridged by a couple of girders resting on the cantilever ends. The bridge thus contains 2 enormous spans of 1,710 feet each between the towers, the vastness of which will perhaps be better comprehended if we suppose one tower to be situated in the Strand opposite Chancery Lane, a second in the same thoroughfare at the Waterloo Bridge crossing, and the third on the Trafalgar Square side of St. Martin's Church. In height, the towers would rival that of St. Paul's Cathedral. On the north shore of the bridge is approached by a viaduct 289 feet 11 inches long, and on the south by one 1,978 feet. The total length of the structure, including the length of the towers, 145, 260, and 145 feet respectively, is 8,295 feet 9.5 inches. The 2 main spans, crossing the 2 channels, permit the passage at all states of the tide of vessels whose topmasts are not more than 150 feet above high water level, for a distance of 250 feet north and south of the central line of the spans. The 3 central towers, to be referred to as the Fife, Inchgarvie, and South Queensferry, each rest on 4 solid piers of masonry, built up from a firm foundation. Viewed sideways, the 4 vertical columns composing a tower are parallel, but when seen from the railway track, a decided taper is noticeable. The batter of 1 in 7.5, which contracts the towers from 120 feet at the bottom to 33 feet at the top, is maintained throughout the structure to the cantilever ends, where the height has shrunk from 330 to 34 feet, and the width from 120 to 32 feet at the bottom. Inchgarvie Tower is longer than the other 2, 260 feet as against 145, for reasons that will be seen immediately. The sides of the towers are strengthened by huge tubular bracings, which run from the foot of one column to the top of its neighbor, and all 4 columns are connected together horizontally, both top and bottom, by powerful ties. In addition to these are a number of smaller bracings running in all directions, giving the whole structure wonderful stability. Nature had favored the engineers by placing Inchgarvie in mid-channel and providing firm matter on which to erect the piers. But, on the other hand, the Forth is exposed to gales, which on several days of the year blow with such fury as to prevent the passage of even paddle steamers. The enormous pressure of a wind, blowing upwards of 20 pounds to the square foot on a structure of the size of the Forth Bridge, had to be reckoned with. The tapering shape of the cantilevers towards their extremities had the effect of offering least surface to the wind where it had most leverage to twist the cantilevers about their supports, and the straddling of the columns further minimized danger from air pressure. But Messrs. Fowler and Baker thought it best to make a slight concession to the elements, by a contrivance that also provided for longitudinal expansion and contraction of the steelwork under varying temperatures. Accordingly, one of the 4 columns in each tower was fixed rigidly to its pier, but the other 3 carried at their lower extremities bed plates, moving over corresponding bed plates attached to the piers. Strong bolts passing up through slots in the upper plates allowed the latter to move slightly horizontally, some in a circular path round the fixed pier, and all in the direction of the center line of the bridge. The 2 extreme cantilevers were so fixed at the viaduct ends as to prevent side play, but permit longitudinal expansion. The Inchgarvie Tower differs from the other 2 in having neither its north nor its south cantilever fixed, and both can therefore exert a twisting strain on the tower. Great care was necessary to make due provision for such movements in the attachment of the suspended girders in the middle of the 2 main spans. They are hung in such a manner from the cantilevers that longitudinal expansion is possible in both girders at their Inchgarvie ends through the medium of sliding blocks, while rocking posts or pivots are provided at both ends to enable them to adapt themselves to any lateral sway of the cantilevers. Inchgarvie Tower, on account of its splendid isolation, is also at a disadvantage with regard to live or train loads. If 2 heavily laden trains pass one another at the end of a cantilever, they exert a great pull on the central tower, tending to lift it from its further piers. In the case of the Fife and Queensferry towers, such a loss of balance is obviated by terminating the landward cantilevers in huge boxes, each containing 1,000 tons of iron and resting on the end viaduct piers. Such a provision was impossible for Inchgarvie, so the engineers increased its length by 115 feet to give the columns further from the live weight a greater counteracting leverage. It is interesting to notice, as an example of the thoroughness with which all the work on the 4th bridge was carried out, as a preliminary operation, 3 wind gauges were erected in the summer of 1882 on the top of the old castle on Inchgarvie, and daily records taken. 2 of these were fixed to face east and west, from which directions the wind would strike the bridge almost at right angles to its longitudinal axis. The 3rd revolved to meet wind blowing from all quarters. The largest windboard, 15 by 20 feet, or 300 square feet in area, had cut in it 2 circular openings of 1.5 square feet area, the one at the exact center and the other at the right-hand top corner, each containing circular plates registering pressure independently of the rest of the board. The fact that on March 31st, 1886, the upper opening recorded only 22 pounds per square foot, while the center pressure rose as high as 28.5 pounds, seems to show that great wind pressures are very unevenly distributed over a large surface. This is confirmed by the records of 2 additional revolving gauges set up on the central towers, where simultaneous pressures varied as much as 10 and 12 pounds between the different piers. The first thing to be done in the actual work of construction was to accurately fix the positions of the main circular piers. Direct measurements, with tape and chain being impossible, the surveyors had recourse to triangulation. A baseline, 4,000 feet long, was laid on the south shore, an observatory built, 3 points taken on the center line of the bridge, and 20 other stations laid down as required. Careful trigonometrical calculations were made, but in order that there should be a minimum of error with regard to the distances apart of the 3 principal stations on the center line, the measurement of the north span of 1,700 feet from the center of the north circular pier on Inchgarvie to the south circular piers on Fife was checked in the following manner, as described by Mr. Westhoffen in his account of the fourth bridge. Footnote, to which account the author is greatly indebted for his information. End footnote. In a straight portion of the North British Railway, a distance of 1,700 feet had been carefully measured and marked, and transferred to high posts at the sides of the cutting. Upon these posts notched knife edges were placed at the two extremities. A fine steel wire, about 1/20th of an inch in thickness, was laid along the span and drawn over the knife edges with a certain amount of stress put upon it, previously agreed upon. Thus drawn up, the wire left a certain amount of sag in the center, which was carefully measured by level and noted. Two narrow copper tags were then soldered on to mark the endpoints. The wire was then coiled up and kept ready for use. The temperature was noted. On the two shores, immediately under the piers which marked the stations, places had been prepared for levels, by means of which the amount of sag in the wire could be fixed. On a calm, cloudy day, with the temperatures about the same, the wire was taken across the North Channel and laid down upon the prepared knife edges on the piers, and with the same amount of sag allowed, the two copper tags soldered on should have coincided with the notches in the knife edges, provided the distance was correct. The results showed a discrepancy. But after the main spans were completed and measurements taken along the girder, the difference was reduced to but 1 inch in the north span and 6 inches in the south. The amount of preparatory work to be done before building operations got into full swing was on a scale proportionate to that of the bridge itself. On the south shore, the high ground was cut into terraces, and on these were erected a shop for fitting the tubular parts of the bridge, another for the lattice work, a drill road, a carpenter's shop, a pattern shed, and a drawing loft, 200 feet by 60, in which, on a blackened floor, full-sized drawings and templates of the various parts of the superstructure were made. By the edge of the water, a sawmill was established. Houses for accommodating a small army of workmen had also to be built, and a water supply provided. Special services of trains and steamers were organized. An efficient system of handling, storing, and transporting materials for 140,000 cubic yards of masonry and 55,000 tons of steel, besides an equal weight of temporary appliances, was devised. A cable for telephonic communication between the various shops and offices at working centers crossed the bed of the Forth. And we may close a very incomplete list by naming the construction of a jetty, 50 feet wide and 2,100 feet long, extending from the South Queensferry shore to the piers of the Queensferry Tower. This jetty was a considerable piece of engineering in itself. It carried lines of rails for conveying stores and steelwork to the Queensferry piers, or to barges plying between it and Inchgarvie and Fife. 10 out of the 12 circular piers, carrying the 3 towers, were constructed by means of caissons and cofferdams. These may be described as contrivances for laying dry a space below water level or preventing a free flow of water over it. In soft ground, a cofferdam is formed by driving down 2 circles of long contiguous piles, leaving between them the circles a space of a few feet, which is filled in with watertight clay puddle. The dam thus formed is provided with sluice gates to let in water when required. In some cases, the water is excluded until half-tide, when the rising pressure may make it expedient to admit water, so as to equalize the pressure on both sides of the dam. When the dam is strong enough to resist high water pressure, it is called a whole-tide dam, and the space inside can be worked upon continuously. On rock, recourse is had to steel-sided caissons, the sides being cut to fit the contour of the rock on which they rest, and their bottom edges made watertight by means to be presently described. In deep water, where outside pressure becomes very severe, an ingenious structure called a pneumatic caisson is used. This consists of an upright circular iron cylinder, resembling a gasometer in outline, built of stout plates closely riveted together. 6 or 7 feet from the bottom, a watertight metal diaphragm, or floor, shuts out the lower part of the caisson from the upper air, and so gives it, when the hole is sunk, the properties of an ordinary diving bell. Leaving for a moment a further description of the caissons, let us turn our attention to the following table, showing the depth of the deepest points of the 12 piers of the Forth Bridge towers below high water. Fife, northwest, 7 feet below high water. Fife, northeast, 7 feet below high water. Fife, southwest, 25 feet below high water. Fife, southeast, 37 feet below high water. Inchgarvie, northwest, 23 feet below high water. Inchgarvie, northeast, 26 feet below high water. Inchgarvie, southwest, 72 feet 1 inch below high water. Inchgarvie, southeast, 63 feet 9 inches below high water. Queensferry, northwest, 85 feet below high water. Queensferry, northeast, 89 feet below high water. Queensferry, southwest, 71 feet below high water. Queensferry, southeast, 73 feet below high water. As each of the piers rises 18 feet above high water, the total height of the structure at the northeast of Queensferry Tower is 300 plus 89 plus 18 equals 437 feet. No dams were required for the Fife North piers. The Fife South piers were built inside steel and wooden pile cofferdams. In the case of the Inchgarvie North piers, stagings were erected over the sites of the piers and soundings taken at intervals of 6 inches round the circumference of a 50-foot circle. An iron belt 3 feet deep and 60 feet in diameter was then constructed, and to this were attached vertical steel plates of a length corresponding with the depth of water immediately beneath. As soon as the hole had been completed, the shell was lowered into place, the uppermost part resting in a groove cut in the higher levels of the rock. Rows of concrete bags were then placed outside, and clay rammed between them and the plates until tight joints permitted the pumping out of water at half-tide, an operation entailing the removal of 590,000 gallons in less than an hour's time. From a reader's point of view, the remaining 6 caissons, the southern Inchgarvie and all 4 Queensferry, working on the pneumatic principle, will be of a special interest, and as such merit a more detailed description. The pneumatic caissons, 70 feet in diameter at the bottom, and of different heights, were erected on the South Queensferry shore, and when complete were loaded with concrete and tools and launched, to be towed to their final resting places. These last had already been carefully surveyed by means of a circular raft of planking and timber box 70 feet across, having a central upright staff and a carriage running on a circular rail laid a foot from the outer edge. Attached to the carriage was a drum of steel wire, raising and lowering a 60-pound weight for taking soundings. The raft was moored in such a position that its central staff occupied a certain point determined by instruments, and soundings were made. At South Inchgarvie, where the foundation is sloping rock, piles of sandbags were arranged at the points of greatest depth, so that the caissons should settle on an even keel. These caissons, after being towed into position, were gradually loaded with deposits of concrete until they began to touch ground at low water. Additional piles of sandbags were then placed below in the air chamber, and the rock was gradually cut away on the high side to make a chase for the caisson to rest upon when loaded sufficiently to lose all its buoyancy at high water. The circular area of bedrock and the supports were then removed by degrees. Let us imagine ourselves furnished with the engineer's permission to visit the working face below a caisson. On reaching the deck of the caisson, we see a powerful steam crane raising loads of debris out of an airlock, at the upper end of a tube communicating with the air chamber 60 feet below. We are ushered into the workman's airlock, a circular chamber with another circular chamber 3 feet 6 inches diameter in its center. The doors through which we entered are then closed tight, and a tap communicating with the air chamber opened until the pressure has gradually risen sufficiently to allow the opening of doors in the central tube. We descend ladders, experiencing a sensation of great oppression on the ears and eyes, and presently find ourselves among the workmen, mostly North Italians, with a sprinkling of Germans, Belgians, French, and Austrians, who have been brought over by Monsieur Coiseau, the contractor, for this part of the work, not as being better physically able to work under such circumstances than Britons, but as more experienced. Powerful electric lights of 200 candle power illumine the chamber, the sides of which slope outwards towards the bottom, ending in a stout steel cutting edge. 2 men, armed with heavy sledgehammers, are beating on the top of a crowbar held by a third. They are drilling or jumping holes for blasting charges. As soon as enough are made, the charges will be inserted and, when every one has withdrawn, after carefully shielding the lamps, be fired from above by electricity. Then the men will descend again and remove the debris by means of the skips that pass up and down their own airlock and well. Under one side of the caisson, where piers of concrete bags support the edge, men are thrusting out sandbags that have served their purpose, and in the gaps we may perhaps see the startled visages of salmon, dogfish, and other denizens of the deep that from time to time are attracted to the glare of the lights within. In the Queensferry caissons, a somewhat different spectacle would present itself. The drills and cement piers are absent. There is no preparation for blasting, for we stand now on more or less stubborn clay. If the sinking of the caisson is still in its earlier stages, we make the acquaintance of the air ejector for discharging the silt that mixes readily with water. A man standing in the muddy mixture lowers to its surface the nozzle of a hose, and another man turns on a large tap that controls the passage of the compressed air of the chamber to the outer atmosphere. As soon as the tap is opened, a rush of air takes place, and the nozzle being dipped into the liquid, some of the latter is carried up by the hose by the momentum of the air and shot out at the farther end of the piping in intermittent spurts. The rate of ejection depends largely on the skill of the operator. On reaching the hard and stubborn clay below the silt, the workman's energies become unequal to the task of removing the spoil by mere muscular effort. The forces of nature are now called in. An hydraulic spade, the invention of Mr. Arol, is set up. A word about this spade. It is, described briefly, an hydraulic ram working at a pressure of 1,000 pounds per square inch. To its lower end is attached a large spade, and to its top a headpiece. 2 men fix it vertically, with its head against the roof of the chamber, and another turns on the water, which with giant strength forces the spade into the boulder clay, detaching a slice 16 to 18 inches deep and 4 inches thick. The spade is then moved on a little, and the operation repeated until trenches have been cut all over the bottom. The air pressure under which the excavators had to work rose on occasions as high as 40 pounds to the square inch, yet not a single death can be directly attributed to these abnormal conditions. The principal bad effect produced by air pressure, says Mr. Westhoffen, appears to be that of severe pains in the joints and muscles of the arms and legs. As these have been in most cases traced to hard work and copious perspiration, and also to too long a stay under pressure, it has been suggested as a probable cause that small globules of air make their way through the skin or between the skins, where they remain and, on the workman returning to ordinary atmospheric pressure, expand, and thereby cause the most agonizing pain in the joints, the elbows, shoulders, kneecaps, and other places. In seeming confirmation of this, the sufferers got instant relief on returning to high pressure. Thus it happened that many of those afflicted with this disorder spent the greater part of Saturday afternoon and Sunday under air pressure, and only came out when absolutely obliged to do so. Various researches were made by members of the medical staff in the endeavor to give relief or obtain a cure, but, so far, not with any degree of success. Owing to the nature of the river bottom, the sinking of the Queensferry caissons was a matter of much anxiety to the engineers. At low water especially, when the cutting edge bore down with greatest force, a sudden settlement was to be feared, and therefore the men were then generally withdrawn, a precaution that on one occasion at least was amply justified, for the caisson, without warning, sank 7 feet, filling not only the air chamber, but also part of the airlock shaft with mud and silt. The most serious accident that took place during the building of the bridge happened to the northwest caisson of Queensferry. It had been towed into position during the high tide, and at the ebb took the ground so firmly that, an unusually high tide occurring soon afterwards, it filled and canted over. The consequent pumping operations were conducted too fast, and before the caisson could be sufficiently strengthened on the inside, the water outside burst in the plates, making a rent about 30 feet long on the lower side. This unfortunate occurrence necessitated the construction of a heavy timber frame round the caisson, and nearly 10 months passed before it was afloat again. As soon as the caissons had reached their full depth, all tools and appliances were removed from the air chamber, and this last filled up with concrete shot down the shafts. Then the caisson above the chamber was filled to low water level, where the granite courses commenced, having at this point a diameter of 55 feet. At 18 feet above high water level, the piers terminate, and are carefully leveled to receive the lower bed plates, which are securely held down by bolts built into the masonry. Piers being ready, the erection of the steel superstructure commenced in the fixing of the skew-backs, or great steel tubes with one side flattened and attached to the upper bed plates. From the skew-backs ran out the lower members of the cantilevers and columns of the towers, the huge diagonal struts uniting the foot of one column with the top of its neighbor, and horizontal girders towards the other piers. As soon as the horizontal work immediately above the pier was finished, the vertical columns were taken in hand. Huge plates, already correctly drilled and shaped, 16 feet long and a half-inch thick, were placed in position by means of cranes. When columns and struts had reached a point 50 feet above the piers, stagings were built on girders 190 feet long in the Fife and Queensferry towers, and 350 feet at Inchgarvie, these girders resting in turn upon very strong box girders stretching east and west from column to column, and raised at each end by powerful jacks situated in the columns themselves. On this manner the need for continuous scaffolding was obviated, and a riveting cage, consisting of a riveting machine enclosed in a cylinder of stout iron wire to prevent loose rivets, tools, etc., from falling with disastrous effects on the workers below, followed the stagings up the column, making permanently secure all the work bolted in position by the men above. The pressure on the rams required to lift the stagings, which at Inchgarvie weighed 700 tons, was 3,920 pounds to the square inch. We read that the first lift of the Inchgarvie platform occupied 18 days, whereas the last, owing to the increased skill of the men, took but 5 hours. Great care was necessary in the erection of the towers to ensure that their lateral batter and center lines should be absolutely correct. From time to time, the structure was checked by means of theodolites, and when any deviation from accuracy had been observed, hydraulic rams were applied to force the tubes into their proper position. Anyone who has tried to bend or straighten the small tubes of a bicycle will have some faint idea of the power needed to master these giant 12-foot cylinders. On the completion of the towers, the lower and upper members of the cantilevers were commenced. The upper members, being in tension, are all straight and of lattice girder work, but the lower, or compression members, are of tubular construction and spring outwards in an arc of polygonal outline, as it was found inexpedient to curve the tubes. The tubes shrink in diameter and thickness as they leave the towers and approach laterally to the corresponding tubes of the nearly parallel member on the other side of the cantilever, so that at its end the cantilever has diminished in breadth from 120 to 34 feet, thereby gaining greatly in power to withstand wind pressure. Both top and bottom members were built out by the help of traveling cranes, which, starting at the foot and summit of the columns, raised material from barges in the river below, placed it in position, and then moved forward. On reaching the ends of the cantilevers, they climbed the upper bow-shaped surface of the suspended girders. These were built out from their ends in a manner similar to that of the cantilevers, and a junction was effected near their centers as soon as the temperature of the atmosphere had expanded the steelwork of the whole structure sufficiently to bring the final bolt holes opposite one another. The false work connecting the girders to the cantilevers was then cut, and the girders rode free in their slides and rocking posts. In the case of the north-central girder, an interesting episode took place. The junction had been made, and the men were cutting the rivets of the false work, when suddenly the remaining rivets, some 36 in number, were shorn by the contraction of the structure, and the plate ties parted with a noise like that of a large gun, shaking the bridge slightly from end to end. The incident caused a little temporary alarm, and lost none of its importance as reported in the papers, but so far from being a mishap was merely an instance of nature saving men a considerable amount of toil. The permanent way was laid on the internal viaduct traversing the bridge from end to end. 4 parallel rail troughs, 18 inches deep and 16 wide, were filled for 6 inches with teak and pine blocks, and on these the plate layers placed longitudinal teak sleepers, securely bolted down at intervals to the blocks. The rails, of bridge section, are exceedingly heavy, weighing 120 pounds per lineal yard. At the sliding ends of the central girders, where there is allowance made for a longitudinal expansion of 2 feet, special ingenious joints are provided which enable the rails to slide backwards and forwards without losing their gauge. On each side of the track is a 4-foot path for the exclusive use of the officials of the line employed in looking after the bridge. Before closing this chapter, which, for want of space, has not dealt with many interesting points of construction, we may notice some statistics, which will escape the charge of dryness in that they help the reader the better to appreciate the nature of the undertaking. Work on the bridge began in January 1883. On March 4th, 1890, the then Prince of Wales formally declared the bridge open to traffic, in a severe windstorm that impressed the company present by its impotence to shake the mighty framework of steel. The 7 years of work represented an expenditure in materials and labor of £3,177,286, the largest half-yearly payment being made in the last 6 months of 1887, when £253,500 were disbursed. The piers carry a total weight of 50,958 tons of steel. Of this, Inchgarvie Tower alone weighs 7,036 tons, or nearly as much as the Eiffel Tower, which could be laid comfortably in either of the 2 main spans, and a column twice as high as St. Paul's laid at its end would barely fill the gap remaining. To sever the top ties of the towers, a strain of 45,000 tons would be required, and Sir Benjamin Baker himself assured his audience at a lecture that 6 of our weightiest ironclads could be safely suspended from the cantilever ends so far as the bridge was concerned. The total number of rivets is at least 6,500,000. Allowing an average length of 2 inches a rivet, they represent a bar 200 miles long, varying in diameter from 1 1/8 inch to half an inch. As many as 4,600 workmen were engaged on the bridge during the busiest times. Among these, accidents were frequent, but mainly attributable to the indifference and carelessness of the men themselves, who, in spite of repeated ocular proofs to the contrary, appeared to think that the fall of a carelessly thrown chisel or other tool would not be attended with disastrous results. We are not, therefore, surprised to learn that in 6½ years no less than 57 fatal and 106 very serious accidents occurred, and it comes as a curious reminder of the unreasonableness of workmen to read that the principal strike was brought about by the fall of a riveting stage, which collapsed because those responsible for its management neglected ordinary precautions while hoisting it. Nothing that can be said will probably more vividly present to the reader the size of the bridge than the statement that the area to be painted once every 3 years, inside and outside, is 145 acres, or that of a good-sized farm. The whole of the outer surface was covered 5 times during construction, once with boiled linseed oil, twice with red lead, and twice with oxide of iron paint. A large staff of men is always at work putting on fresh coatings to withstand the corroding action of the salt sea breezes. The railway passenger is in a particularly unfavorable position to view the bridge as he passes. By putting out his head, he can only see a long vista of huge tubes and girders, foreshortened in such a way as to lose their full impressiveness. Moreover, he is at an elevation near the center of the total height. To get a just scenic idea, one should approach the bridge by boat on the Forth, so as to take it in flank. Then what a stupendous structure it is, a thing of huge lines and triangles, its geometrical repetitions out of keeping with the lovely landscape, and yet having a grandeur of their own. With what pride must the engineers have looked upon the finished structure, the child of their brains, remorseless consumer of steel and stone, reared amid the clash of monster machines, nursed by small armies of workmen. What were the 8 years of battle with wind and wave, and their trials and struggles, now that the last rivet had been driven in, and the track opened for the iron steed, a mere fly among the steel web of the bridge, yet the whole built for the passage of the fly. Surely the Forth Bridge is the incarnation of engineering romance, in which brain and metal and stone have joined hands with the powers of nature to triumph over the obstacles placed in man's way by nature herself. Mr. Westhoffen, the engineer in charge of Inchgarvie, has an eye for the picturesque, and the author feels that he cannot do better than quote in conclusion his eloquent description of the view to be had from the bridge. The view from the summit of the central tower on a clear day is magnificent. The broad river itself, with craft of all sorts and sizes, in steam or under sail, running before the wind, cutting across the current on tack or lazily drifting with the tide, is always a most impressive spectacle, upon which one can gaze for hours with an admiring and untiring eye. And such it is, whether viewed in the glory of sunrise or sunset, in broad daylight, with the cloud shadows flying over the surface, and 1,000 ripples reflecting the sun's rays in every conceivable shade of color, or in the soft haze of a moonlit night. The sunsets in summer are always magnificent, whether due to Krakatoan volcanic dust or to the vapors of the distant Atlantic, but there have also been many sunrises in early autumn when a hungry man could forget the hour of breakfast, and one could not find the heart to chide the worker who would lay down his tools to gaze into the bewildering masses of color surrounding the rising light of day. An unbounded view more than 50 miles up and down river. At night, too, a sight is presented not easily forgotten, the flashing lights of the May and of Inchkeith, and many others stationary, such as the harbor lights of Granton, Leith, New Haven, and Burnt Island, combine to form a beautiful picture. At times of continued east wind, when large and small craft run for shelter in the Forth, it is not unusual to see from 150 to 200 vessels anchored in the roads, and the long straggling lines of their masthead lights give the appearance of a busy town, of many streets having suddenly risen from the waters. On Jubilee night, 21st June, 1887, although the atmosphere was somewhat thick, 68 bonfires could be counted at one time on the surrounding hills and isolated points, while the great masses of the central tower of the bridge, lighted up by hundreds of arc lights at various heights where work was carried on, formed, with their long-drawn reflections in the water of the Firth, 3 pillars of fire, and afforded a truly wonderful and unique spectacle. End of chapter 4.